So hello. As Steve said, I'm Chris. I'm sure most of you know that. I'm kind of rounding off the three ESD postgrad presentations here, looking at the effects of climate change, sea level rise on the geomorphic response of coastal gullies. So I'm going to give a brief outline of what these incised coastal gullies actually are and why they're so sensitive to climate change. Have a brief look at kind of some general projections of climate change for the southern England, South UK, and then look at some more kind of focused projections for my study site before going into how that all kind of files into the modelling that I've been doing, and then put up some initial results that are very initial. Got them Monday, so very initial. So incised coastal gullies, as it says there, steep-sided deep fissures cut by a stream through soft rocks descending over a cliff edge towards the sea. My study site is on the Isle of Wight, you can tell by the two pictures and their captions. However, these features are found across the globe, with examples on the shorelines of the Great Lakes in North America, New Zealand coastline, and some of the coastlines in Hawaii. Incised coastal gullies are part of this family of incised channels that represent disturbed landscapes undergoing rejuvenation. And this disturbance, in most cases for incised channels, is caused by base level change, and in coastal locations this base level change is driven by cliff retreat and sea level rise. This diagram quite neatly and succinctly outlines the key processes driving these features and their evolution. And as you can see, the two main processes that operate here are cliff recession and nick point recession. When the two processes are in equilibrium, we get these this kind of stable band. I should say here that chine is the Isle of Wight term for an incised coastal gully. So if you see the two words pop up, they're interchangeable and they mean the same thing. So if when these two processes are equal, we get these stable chines. If one exceeds the other, then these gullies tend to decay or grow. Cliff recession acts to truncate gully systems by shortening the length at the coast, whereas nick point recession induces headwards erosion inland and extends these chines inland. So as nick point recession rates increase, you see the chine grow inland. And it's these processes which are greatly affected by climate change. Nick point recession is driven by in-stream discharge, which is driven by changes in precipitation. So changes in precipitation are going to greatly affect this process. Similarly, we're going to see changes in sea level rise and wave height and wave climates, which are going to impact on cliff recession rates. So it's understanding these balances in the future that is kind of what I'm looking at in this work. So what climate change can we expect to see in the UK? I would say these are kind of UK-wide projections to start with. And these come from the UK Climate Projections 09 report. With regards to precipitation, we're seeing an increased seasonality in precipitation, with a change towards more intense winter precipitation and less summer precipitation. And also on top of that, we're seeing extreme precipitation rates up by about 25%. So we're seeing a switch towards more extreme events. And it's these extreme events which are key for geomorphic change within these systems. As well as that, these systems in coastal locations are going to see rises in sea level. Around the UK, this can range, it's predicted to range anywhere from between about 12 centimetres to 72 centimetres by the end of this century. The Solent and the Isle of Wight is expected to experience sea level rises towards the high end of that range, so about 65 centimetres upwards. Coupled with changes in wave heights, which in the physical systems are layered on top of these sea level rises. So we're seeing a mean average drop in wave heights, anywhere between a drop of 35 and a slight increase in 5 centimetres. But again, it's these extremes in wave heights that are going to be driving these processes that we're going to see on the Isle of Wight, with extreme wave heights expected to increase by about 10 centimetres. They are UK-wide projections. However, for my study, we need to kind of drill down into what's actually going to happen onto the Isle of Wight coast. So to get local scale projections of climate change, we've employed 2 global climate models. We've got the HAD CM3 and the Canadian Global Climate Model version 2. They've both been widely used in providing projections for UK climate. And they're forced under 2 different emission scenarios. If you can see on the graph there, we're using the A2 emission scenario, which is the red line, which is one of the high-end emission scenarios, and also the B2, which is the orange line, and is often called the business as usual emission scenario, and is towards the lower end of what the IPCC reckon is the possible range of emission scenarios. So we're getting a spread, and we're covering the spread of plausible climate change. These have a temporal resolution of daily resolution, so we're getting daily changes, which is what feeds into the model that we're using. However, the spatial resolution of these models is 300 kilometres squared, which isn't very handy when you're looking at a 3 kilometre square catchment on the Isle of Wight. So we then need to drill down further and downscale those towards these kind of spatial 1 kilometre squared scales. And to do that, we use the statistical downscaling model of Wilby 2002, which can be best described as a regression, a hybrid regression weather-generated downscaling tool. What it does is it compares large-scale climate forcings over a baseline period of 1960 to 1990 with observed climate variables from your point, so from the southwest Isle of Wight, over the same period, and then uses those regressions to force the weather generator to downscale the global climate model outputs to the point source. So it's using historical relationships to force future climate change with changing forcings. Doing that, we produce 4 ensembles, so the 2 climate models and the 2 emission scenarios. So we have 4 different scenarios that we're modelling. And what we see is that the downscaled results agree with what the UK climate projections data have said, which were on a few slides previously. So we're seeing sea level rises at the higher end of that range that they projected, an overall decrease in mean precipitation, but increases in extreme precipitation, and the same sort of story with significant wave heights. And that all feeds into the modelling framework. I've employed the child landscape evolution model, which has been modified to include a coastal retreat function. Previously, none of these suite of landscape evolution models available have these processes inbuilt, so we've built one of these and coded it and added it to the model. It's run over a 100-year period, so we're looking at the next kind of century climate change. Initially, it's been applied to Grange Chine, which is on the southwest coast of the Isle of Wight. It's the largest of these features on there and has a contributing catchment area of 12 kilometres squared. If you remember back to that big diagram at the beginning, it sits nicely into that growing chine area at the moment. And the selection of this chine allows us to see the trajectory of one of these kind of more stable, persistent chines under climate change to see where that will end up in the future. At the end of these 100 years, get the model outputs and we can extract metrics, so we can look at the amount of coastal erosion, the extent of the gully, whether it's shrinking or growing. We can take measurements for gully incision rates, bank angles, gully area. We can extract a lot of these metrics and use them to kind of piece together what's actually happening to these systems. So let's have a look at these results that I haven't really had much time to look at, so I'll put them up and talk about them as best I can. First one, we'll look at how the model is predicting coastal erosion along the southwest coast of the Isle of Wight. And what we have here is two probability distributions for both of the Hadley model runs under the two different emission scenarios. So we have the A2 scenario, this high-end scenario in blue, and this B2 scenario, the more conservative scenario, in red. And what we can see, similar to some of what Simon was saying in his presentation, is that these mean rates that you can predict from these models might not actually be as representative as you think. The dashed line I should add on that graph is the current rate of coastal erosion. So shifts to the right of that line is an increase in rates, and to the left is a decrease in observed rate. So yes, as you can see, the mean rates up here being skewed by the kind of extreme events shifting these towards the right-hand side. But actually, the most likely rates, given the probability distributions, are kind of nigh on what's happening now, if not slightly less. But we're seeing the differences between the emission scenarios coming out, with the high-end emission scenario providing more extreme and kind of higher levels of change than the B2 emissions. What we can do with these is pick out kind of likely scenarios. These are using the IPCC terminologies. So here, likely means anything with a great probability greater than 66%. So you can tie this in with what the IPCC is saying. The ranges that are initially coming out are quite high ranges because of the spread of the distribution. So coastal erosion under these scenarios anywhere between 1.6 and 1.62 metres a year. So you can kind of bound what is an expected rate of coastal retreat along this coast. If we then add in the kind of headwards erosion, we get measures of how these gullies are going to change in extent under these two scenarios. So this is the actual length of the gully from mouth to source changes. The dashed line is 0, so it's stable, it stays the same in the process of keeping rate. What we're seeing here is that under the A2 scenarios, we're seeing a decrease in gully extent, so coastal erosion is outpacing nick point retreat. Under B2, seeing slightly the opposite, when actually nick point recession is able to keep pace with coastal erosion and maybe actually exceed it, and we might see, likely to see a little bit more of a growth in these systems. But again, we're getting this huge tail off towards the extremes. We might actually see these systems being wiped out altogether. So the uncertainty and kind of bounding what is a likely response to these systems is going to be key when we've got more of these results and we can kind of get a bit more of a handle on it. Finally, what I want to do is give you an idea of the kind of analysis I want to do with some of these results. It's kind of picking out the climatic drivers and what's causing these changes. So if we take this example of coastal erosion, what is it about the inputs to the model that is causing the largest coastal retreat, or what is the likely kind of driver that's causing these retreats? As an example here, sea level is often cited as a key driver of coastal erosion, and has often been looked at in detail as the rise in sea level is going to be the key change in coastal erosion. However, if we look here, this is the B2 scenario. It's the only one I've got results for, so it's the B2 scenario. It doesn't look like the higher rates of sea level rise are providing the higher rates of retreat. So the other climate variable that we can look at with regards to this is the wave climate. So if we take a look at the wave climate with relates to sea level rise, what we've got here is a measure of the extremity of the wave scenarios. So picking out the 95th percentile wave height, obviously those with the higher 95th percentile are likely to have more extreme wave climates, or be modelling more extreme wave climates than those lower ones. What you can see here is there's a much clearer relationship between the extreme wave heights and coastal erosion. So hopefully what I want to do when I've got more results is kind of drill into these with regards to the other metrics and kind of pick out what is going to be driving the changes in these systems. So it's just an example. So just to kind of wrap this all up, Southern England, the Isle of Wight, as I'm sure you're all aware, is projected to undergo changes in climate. And this change is going to impact on the geomorphological processes operating on these landscapes. So understanding these relationships is going to be key in the future. Along the Isle of Wight, coastal erosion is likely to be anywhere in those ranges. It is a large range, I admit. It's going to be somewhere in there. And that will result in gully extents of changes between plus 30 and minus 125 metres. And finally, hopefully, we'll be able to pick out what is actually causing these drivers, or what is driving these changes, and kind of pin down specific responses to these features to climate.
Thank you, Chris. Questions? Okay. Well, all right. Yeah. No, Gary, go and start with
this is coming from
the non-supervised.
non-expert background. How the inside gullies then, so you change extents, I understand how they could increase, but how would one decrease? Is there something filling it in, or is it just completely collapsing? Or?
So it's a decrease in extent, so it's a decrease in length from the mouth to the head cut at the top.
Right.
So you get an extent when that head cut encroaches in land, and a retreat when coastal erosion chops off the coast, so it moves back.
This is a question from a long time ago when I did my BSc in geology. What's the fact? Have you considered the isostatic land measures? Because you didn't mention
Yes.
it at all, so
No,
I'm just curious how that's built in.
Yes, they are relative sea level rises, so they do have a. Is that the one? Yeah, they do include an isostatic rebound kind of effect on them. I can't remember if that's relative or absolute. This one, but yeah, it is incorporated.
Back to the first year for you, then, Chris.
Yeah.
It's just, I suppose, a general question about the scenarios, because obviously the scenarios have been developed a wee while ago now,
Yeah.
pre-economic meltdown, etc.
Yeah.
And I mean, there's a lot you can think about scenarios, but I suppose a very simple technical question is, having done all the work, you've done a lot of work to get to this stage where you can start to create output. Is it pretty simple to go back to have a look at a range of other scenarios, or when the next IPCC comes out, etc., it's bound to be a range of very different, one would guess, scenarios?
Yeah.
Is it pretty straightforward then to go back in and having done this groundwork, which is obviously a lot of work to get to this stage?
Yeah. The relationships, the climate scenarios are driven by these historical relationships between the large scale and the point source. So those relationships will stay the same. It's then a case of just obtaining kind of daily outputs for different scenarios. So if they produce more, then it's a case of running that statistical downscale model with the kind of renewed emission scenario.
Is that a reasonably straightforward thing to do?
Fairly, yeah. It's not going to collapse if that's the case.
It's a cunning strategy for getting the next funding, isn't it?
Exactly, yeah.
Any other questions quickly? Okay. Thank you again, Chris. Thanks.